Disseminate, the computer science research podcast.
Hi, and welcome to Disseminate, the computer science research podcast. I'm your host, still not Jack Wadby. You may recognize me from the previous episode. I'm, of course, yours truly, Bogdan Stoica, but you can call me Bo if that's a mouthful. Today, I'm joined by two guests, Rohan Padhye, who's an assistant professor at CMU, where he leads the PASTA Research Lab, and Leo Lee, a final year PhD student advised by Rohan. They're here to talk about software testing woes, concurrency bugs, and their most recent paper published at OOPSLA this year, Fray, an efficient general-purpose concurrency testing platform for the JVM. Leo is also on the tenure track job market for this year, so please check out his research and papers. Reach out to him if you're in the hiring committee or if you know your department is hiring. Rohan, Leo, welcome to the show.
Thank you very much. Glad to be here.
Thank you.
So let's dig in. I am always curious when we get new guests on the show to talk about how they actually found their way into the research area. So for you guys, that is software reliability more generically. So how did you end up in software reliability, and why did you choose CMU and why PASTA?
Yeah, so I've always been interested in doing research on anything to do with software, mainly because it's easy to imagine myself as the customer or the end user for the research that I do, because I build tools for software developers, and I've been doing software development for a long time. Specifically, the area of program analysis is something that I've been looking into for I think over 12 years now. I think 12 years ago, I took a class called program analysis when I was a student in a master's program back in India. And here I am today at CMU as a professor teaching a class called program analysis. So this is something that I really enjoy doing. And I've also worked at various different companies in different roles and have seen the kinds of code that actually runs in production and powers many of our software systems that we all rely on. And so I sort of understand the importance and impact of research that can improve software reliability. CMU is really special. It's obviously a well-known university in computer science overall, but specifically in the area of sort of software analysis. It's very special because we have our own PhD program in software engineering. CMU is also weird because we have many different departments within the School of Computer Science, one of which it's called the one that I'm in. It's called the Software and Societal Systems Department. And so we essentially have the largest collection of researchers in the field of sort of software analysis and engineering probably anywhere in the world. So it's really amazing. And we also get to work with amazing students such as Leo on these kinds of fun projects. And that's what's really exciting.
Yeah, so for me, I started to work on software-related research starting my undergrad, and where I was working with Karin, who was professor at University of Calgary. And so we were building static analysis tools for Swift. So that was a really fun experience because one thing I got a chance to experience what the real world bugs that issue are, and also I got a chance to contribute to open source projects. So I think that actually motivates me to continue to work on this area. And also I chose CMU. Part of the reason is that CMU has a really big school where you can work on many different areas and you can find experts in pretty much every domain. So for me, I'm especially interested in software analysis, but also I want to apply software analysis to real world applications. So I'm now currently code-wise by two professors. One, Rohan Padhye, he's an expert in program analysis. I'm also advised by Stoica, who is an expert in system network research. So I think there are many places where you can actually find experts in pretty much every domain. So that makes me thinking CMU is like a great place to do this kind of research.
Sounds like you both have a similar path, working on program analysis during undergrad or during your master's, then working in industry and on more applied research projects, continuing this line of research in your PhD and beyond. So I'm curious, your work focuses on a or at least in recent years, have been focusing on a particular type of issues, concurrency bugs, which have been studies for decades. You've both been working in this area for quite some time. So why are concurrency bugs still a problem in industry today, given all of these extensive efforts, and what's still out there to fix?
That's a great question. Yeah. And I think there's a sort of a two-part answer here. Firstly, concurrency bugs are just like harder than bugs in like sequential programs for humans, for developers to sort of reason about, mainly because of the way we're sort of used to thinking about code. We write code as like sequential lines in a file. We're used to imagining code executing as like traces of instruction by instruction. Concurrency bugs often arise due to race conditions between various components interacting in a way that's really hard for humans to imagine, and therefore they're rare. They often escape testing unless you sort of are looking for them specifically. And also, if you actually do encounter them, they're really hard to debug because the order of interaction between components is not always very easy to sort of control or reason about. That's from the point of view of the source of these bugs. But as you said, like researchers have been studying techniques to detect and discover and reproduce these bugs for decades. Why are we still facing these issues today in sort of most real world applications? Well, I think there's a little bit of nuance to this aspect. This is my personal opinion, and I think an opinion that Leo also shares. There's been a lot of work in academia on developing algorithms for finding various kinds of race condition bugs, everything from data races in multi-threaded code to race conditions in distributed systems. But the real world code is complex, it's messy, and often the challenges in finding concurrency bugs is not just about having the right algorithm that can search the space in an efficient way, but it might sometimes be just having platforms that allow you to run any of these algorithms in the first place. A lot of concurrent programs rely on third-party libraries. They rely on fancy features such as asynchronous computation and futures. They might be running distributed systems. They might depend on external services. They might be stateful. And a lot of the academic work sort of makes, in some cases, simplifying assumptions about how these algorithms can run, under what context they can run, when they will actually work. And often the engineering of practical tools is sort of left as an exercise for the reader, let's say it that way. And so, engineers who work on, who build real systems sometimes still find it hard to use any of this research that we've, as a community, been doing for many decades in actually finding these sorts of race condition bugs in their code. And so part of our motivation for this work was to bridge this gap.
Yeah, Rohan gave a really nice point. I think there's one thing I want to mention is that in many cases, when we think about building a system or designing a new programming languages, in most cases, we think about usability, we think about performance, but we don't really think about debuggability and testability at the very beginning. So in many cases, testability and debuggability are actually an afterthought. After we already achieve this performance, after we achieve this like programming features, then we think about how we can debug them, how we can test them. So concurrency is actually a really good example where people start to use concurrency to chase performance. But after they achieve this their performance goal, they notice, hey, actually, those concurrent programs are extremely hard to debug and test. So this is also my research goal. I hope in the future we can bridge this gap by helping developers to think about how they can debug and test this kind of program easier.
Awesome. So this is so much my experience with having a grown-up job before joining my PhD program and working in the industry as a software engineer. Leo, I think you hit the nail on its head. Debuggability is an afterthought many times. I would argue performance as well, but that's a separate discussion, maybe a separate podcast episode. And I think it's as a community, not only research community, but a software engineering community, systems community, we need to start thinking about debuggability as built into the system design process. And as you both mentioned, maybe have this as a platform, or have these as at least abstractions that developers can and researchers that they're building research prototypes can reason about. Which brings me to my next question: is this the core idea behind Fray, your most recent system that got published at OOPSLA this year?
The idea of Fray is very simple. We just want to provide a general purpose click button thing for concurrency testing in JVM. The reason we picked JVM is that we already had lots of experience in Java and the JVM platform. So we feel most comfortable about this. And so we actually had a very simple goal for this paper, for this project.
I see. Rohan, I think, there's for you working in industry and now being in academia, I think, you've seen both sides of the problem, the struggle that researchers have with coming up with these tools to make them more usable and less false positives and whatnot. And then software engineers struggling to make sense of the output of the tool. How does this new project bridges this gap? I know, from skimming through the paper that Fray actually has real users and as Leo mentioned, finds bugs in open source software that software engineers care about.
Yes, absolutely. And I think right from the outset, our goal was to make the tool that's sort of easy to use. And so we upfront had very strict requirements of not having to impose a lot of sort of manual burden on users to have to set up their projects to be able to use whatever solution we're building for finding concurrency bugs. So the way that Fray works is that it just works off your existing unit test. So we actually sort of surveyed a lot of real world software projects, things like Apache Kafka and Apache Lucene, Google Guava libraries, etc. And we saw that it's actually quite common for Java developers to write unit tests that do have some sort of multi-threading in them. So for example, I can sort of simplify this and say, let's say you have a parallel sort algorithm. There are unit tests which would just say, spawn a bunch of threads, run your parallel sort, wait for all the threads to join, and then check that the result is is a sorted list, right? And so it's sort of a simple concurrent test, but traditionally the way that these users have been checking the correctness of these concurrent algorithms is simply to run these unit tests multiple times. It's sometimes called stress testing. So what we wanted to do is to leverage these sorts of existing tests, right, and not have developers write any sort of new information in terms of like manual annotations or having to learn a new DSL. We just wanted to take these existing tests and say, we have a tool that will allow you to run this test in a way that you can specify how the various threads in your application would interleave, and you can run one or more search algorithms. So it could be the systematically search for all possible interleavings. That usually doesn't scale. Maybe just do a random search, or run one of these fancy algorithms that academics have been developing over the decades, like partial order sampling or some other well-known algorithms. And so all of the the magic is sort of under the hood. From the user's point of view, they're just running their existing tests. They're pressing a button that says run them with Fray. And then if we find some thread interleaving that causes their test to fail, either their assertion fails, they get an unexpected exception, or their code just hangs with a deadlock, then we give them a replay file that says, here's a file with which you can actually reproduce exactly the same behavior that you saw when running with Fray. And so that could rerun their existing test with a specific sequence of thread interleavings that will show them how that buggy behavior manifests. And so we found this paradigm to be very natural for users to leverage, and that I think helped us, help us and the tool gain traction really quickly with real engineers.
So what you're saying is you built a concurrency debugging platform as a service, right?
Yeah, something like that. Yeah,
yeah, no, that's much needed in both in industry and our research community. One of the woes in working on concurrency bugs and trying to build on others' tools is, well, of course, concurrency bugs are non-deterministic, but turns out that the bug finding tools are also non-deterministic and hard to work with. And it sounds like Fray is trying to bring some much needed predictability in this space. You mentioned real users and open source software that the community cares about. But before we get into the practicality and usability of Fray, I wanted to take a step back and maybe tell a bit the listeners, what type of concurrency bugs do you tackle? Is it all types of concurrency bugs or a very particular subset? And, as a person that has written programs, software programs before, and I'm familiar with having to write tests. You also mentioned, Rohan, that developers usually write tests with some concurrency built in. Why aren't those sufficient? So I guess what type of bugs does Fray tackle, and why they cannot be surfaced by existing infrastructure that software engineers built?
So with Fray, we're looking for race condition bugs, which broadly defined just means some undesirable behavior that manifests under some thread interleavings, but not necessarily all of them. We don't actually have any sort of special logic or semantics to say we can detect a specific kind of bug in your program. We expect that the existing tests that the developers have written have some sort of assertions or some property that they're checking that ensure that the software is behaving correctly. But from experience, the kinds of bugs that we actually do end up uncovering deal with things like atomicity issues or ordering violations. So atomicity issues are those where a program is maybe performing a set of operations that ideally should all occur without any other interference. But in practice, those operations could actually interleave with other threads that are interacting with shared memory. A classic example of this is even if you use something like a concurrent hash map in Java, which is a thread-safe data structure, a common sort of buggy pattern is where you might check, is there a entry for this hash map at some key? And if it does not exist, maybe I will write a new entry. But in between these two operations, another thread could come in and interleave and sort of manipulate the hash map in a way that you actually get undesirable effects. The other thing is things like ordering violations, which means that applications that expect a certain sequence of operations to be run in a certain order, but actually there might be some thread interleavings where you actually end up with a violation of whatever protocol the application expects. And this often arises because the developer may have had some assumption or understanding of what state the program is in after a certain sequence of operations, but maybe that state either gets corrupted or you sort of end up having a state transition that was not in your original protocol design. And so often these are like design bugs, which are not very trivial to fix. We sort of distinguish these kinds of bugs from simple data races. So a lot of academic work has focused on this data race detection. So, just for the benefit of our listeners, I'll, sort of precisely define a data race as, a situation where you have more than one thread accessing the same shared memory location, like let's say, a field of an object or a global variable, and at least one of those threads is performing a write operation. So you have like a read-write or a write-write conflict. And there's no synchronization between these threads, right? So there's no use of locks or no use of like special keywords like volatile. And these kinds of data races are bad for many reasons. And there's a lot of research focused on trying to find these data races. In Fray, we take the conscious decision to say we don't actually care about data races. We're actually trying to find concurrency bugs in programs that otherwise may be well synchronized. And there's a couple of reasons for this. One is that there are lots of data race detection tools out there, and secondly, it's also not that hard to sort of fix data race bugs, right? If you find a data race, usually the solution is add some locks, add some synchronization, and you're sort of done. And so we were targeting these harder bugs, like protocol level bugs, or where the issues are usually more in the design aspect, and these are trickier for developers to reason about and to debug and to fix. And so our tool sort of helps bridge that gap.
I see. So and feel free, both of you could chime in here. To me, it's a bit surprising every time I read about concurrency bugs in Java, because Java has such a wide array of features that help developers write and reason about concurrency in their program. But still, I feel, at least in my limited interaction with C, C#, Java, Python, I don't feel that limited interaction in terms of concurrency bugs. I don't feel that there are fewer concurrency bugs in one programming language than the other. Why do you think that despite all these new features and useful features in Java, we still face similar concurrency bugs that I used to face when I was writing C?
I think one reason is that concurrency bugs manifest because of timing. And it's really hard for a developer to reason about timing, especially when they are interact with a large and complex system. So for many bugs, Fray found was actually like one thread, it is touching a state, while another thread, which is very far from the current thread, like by far, I mean, like the file that implements that thread is not located in the same package or in the same same class. And also with the location, the time the other thread is created is also very far from the current thread. So like in order to understand the complex interleaving across different threads in a complex system requires a developer to memorize the like all kinds of interaction across files, across threads. So I feel this part is very challenging. And another thing is that this is non-deterministic, meaning that after I implement my feature, I can run the program, I can run the task, but the bug will not like appear immediately. It may only appear when you have a high workload server, when your CPU is throttled, or when you run it on a very special hardware. So I think all of these facts adds to this complexity of debugging a concurrent program.
And if I can add to that, Bogdan, you mentioned the word performance some time ago, and while Fray doesn't specifically look for performance bugs, I think one of the reasons why we have so many concurrency bugs out there, even in languages that have nice abstractions for writing current code, is that developers often end up doing really crazy things to squeeze performance out, because there's a trade-off between clean abstractions and performance in many cases. And so if you want performance, you sometimes have to write a little bit more low-level code than what some of the high-level libraries, the kind of APIs that high-level libraries provide. And so a lot of the bugs that we've seen have been in sort of these infrastructure layer libraries, things like Kafka or like Google Guava, which is a set of libraries which are trying to provide higher-level functionality to their clients, but they do so using slightly more high-performance algorithms that deal with like low-level primitives. And that's sort of where you run into this kind of similar trap that you might run into if you were trying to write concurrent C code, as you said.
Right. So timing issues being non-deterministic and trying to squeeze performance are definitely factors that contribute to having more concurrency bugs. And I feel that as you both mentioned in earlier, that Fray is not actually trying to specifically trigger a particular pattern or a particular bug, but rather be a little bit more broad. Having said that, Fray finds different categories of bugs, and I'm curious if you could first maybe talk about the high-level design of Fray and what's the process of finding, how does Fray help developers find bugs, maybe not necessarily in terms of techniques, but rather in terms of abstractions.
So yeah, actually, again, like we are trying to make Fray push button and easy to use, and so to achieve this goal, we did lots of effort to make Fray easy to use. And currently, if you are like your project use Gradle or Maven, we already provided a Gradle and Maven plugin, and it will set up the Fray tool for you. And the only thing you need to do is that if you're using JUnit, you can replace the test annotation with concurrency test annotation. And if you are using other testing framework, we also provide a wrapper so that you can launch Fray by calling a simple method call. And the way Fray works is that Fray will instrument your application with small logs. And those logs will cooperate with each other so that it will only let one thread run at each time. So this allows us to exhaustively explore all possible threat interleavings in your application. But as we mentioned before, systematically exploring all possible threat interleavings is like really hard. It's really time consuming, especially for real world concurrent programs. And we also provide more advanced searching algorithms. So like PCT, POS, and SURW, those are all like well-studied concurrency testing framework, and they are proven to be more efficient in terms of bug finding. So in this case, we believe finding bugs is more valuable than proving correctness, because we're hoping this we are positioning Fray as a useful bug finding tool, similar to fuzzing. So once a bug is found, a user can deterministically replay that bug. So we also actually implement debugger plugin inside IntelliJ, and like a user can visualize the timeline of each thread and can understand how different threads interact with each other that leads to the final bug or final failure. So yeah, we are actually doing more currently, so to make Fray easier to use, and we constantly improving the user experience using Fray.
Awesome. You mentioned in the very beginning, and this is super useful. Thank you for walking through the use cases of Fray. But you mentioned something very interesting. It was actually two things, but I'll start with the one that I find most interesting. You said that concurrency testing is always trying to balance the tension between coverage and state explosion, and whenever you're trying to explore thread interleavings, you end up with state explosion. Could you tell us a little bit more about the trade-offs you had to implement and in order to balance this tension?
Yes. So we actually did lots of efforts trying to reduce the search space. Actually, starting with all like data race with Fray assumption. This is already an optimization we want to make to reduce the search space. After we have data race Fray assumption, we only need to perform thread interleaving around those before concurrency primitives. So this actually aggressively reduced the search space for us, but this still provides a soundness and completeness guarantee for us, meaning that like every time Fray finds a bug, this bug can appear in real world scenario from the original program, and like every possible concurrency bug in the real world application, Fray can find some thread interleaving that trigger that bug. So this is one thing we did to reduce the search space, but even with that, systematically exploring all possible thread interleaving is still challenging. Like for example, for many Lucene Kafka bugs, so even running one iteration takes a couple seconds. So think about the search space is around 1 million thread interleavings happened in one single test run. So, but we still want to find bug faster. Like doing random walk is the baseline we have. So every time you can randomly pick a thread to run. But as we all know that concurrency testing is actually a crowded area and has been studied for like many years. And there are already very nice algorithms are proven more effective in finding bugs. It's just that there aren't practical framework for developers are using them. So now we actually bring those algorithms to the developers, and developers can just use those algorithms to test their concurrent programs and find bugs more efficiently. And even better, we actually designed Fray in a way that implementing new concurrency testing algorithm very easy. So we provide a uniformed interface for developers to implement them. We already implemented many of them. So we know that implementing new algorithm is actually very easy inside Fray.
Awesome. So Fray is not only a bug finding platform where you as researchers have already implemented several techniques that could trigger concurrency bugs, but it's built in such a way that you allow developers to write their own random walks if they want, or their own fault injection, I'm assuming, or delay injection, whatever they feel it's appropriate for their scenario, which is, I think it's great. It's something that I guess both he and Rohan were mentioning in the beginning, not only the usability but the flexibility of those platforms, and the fact that developers can now can implement something that they know, or they're much easier for them to understand, or maybe very specific to their scenario, which I guess makes Fray a very versatile platform. So Fray uses a collection of algorithms and techniques to surface all these concurrency bugs. But I'm curious, how do you come up with the workload to run the programs and get them into a faulty state? What are you using for inputs? Are you relying on existing tests, or you're hoping that developers will write their own tests using Fray? Can you walk us through this?
Yeah, so this actually went back to the motivation of this project. So as Rohan mentioned, we explored this popular concurrent Java programs, Kafka, Lucene, Guava. There are already plenty concurrent unit tests used running in their CI pipeline every day. So our goal was not trying to provide a framework so that developers can implement new concurrency tests. Our goal is to implement a platform that can just reuse those existing concurrency tests. So it turns out these concurrency tests are actually sufficient to test many concurrent features inside the existing framework. It's just lacking of a better testing framework that can surface those bugs. So in our evaluation, we found like more than 18 bugs from just by rerunning all the existing concurrency tests in those large scale applications. So that's how we did for Fray.
Yeah, if you want, I can provide some numbers from our paper. We actually saw that there were 2,600 or so unit tests across the three projects I mentioned before: Apache Kafka, Apache Lucene, and Google Guava. These are widely used, sort of software libraries or frameworks. And there are 2,600 of their unit tests that had some sort of concurrency in them. So they, spawned some threads, did some work, joined the threads, and checked the result. And these pass in, CI usually every day, as Leo mentioned. But with Fray, we found that there were 363 of these tests. So that's a pretty large fraction, almost, I guess, somewhere between 10 and 15% of these tests that could actually fail given a certain thread interleaving that we can now, deterministically replay and show the developer saying, here's a specific interleaving under which either the assertion fails, or you get like an unexpected null pointer exception, or you get a deadlock and the whole test hangs. And so this was definitely very surprising to the developers, which is why we got some traction in having many of these bugs fixed. So there's lots of tests are failing. I think the root causes, as Leo mentioned, were around like 18 unique bugs that we filed in these repositories. But going back to your original question, Bogdan, so we, these tests already were pretty good, right? And the developers wrote these tests as a way to cover various functionality in their code, and so they sort of pick their own loads, so to say. And Fray just helps find the right interleaving that can maybe find some bug. What could be challenging is if you actually end up having a load that's intentionally designed to be like a stress load, right? Where you generate, if you're spawning like tens of thousands of tests, or you're like, running a very large workload in a loop, that can actually become a little bit problematic for Fray, because the state space research would really explode. And so we sort of focus on these like unit tests, not end-to-end system level stress tests for searching over interleavings.
Thank you, Rohan, for mentioning this. Actually, one of my next questions was about Fray's impact, but I'll hold off on that a little bit. You both mentioned two interesting things, and I guess this is interesting to me, but I hope listeners also find is interesting. The fact that these software applications already ship with tests that are meant to exercise concurrent parts of the application. So developers are aware of at least some bug or failure patterns that they can surface in their application while their application runs in production. So they try to, get ahead of this and mitigate. But still, writing tests is not sufficient. And I think this is exactly what Leo was mentioning a little bit in the beginning, that it's just incredibly challenging to reason about concurrency bugs by just looking at the code. You have to keep in mind all the various timings and interweavings that could occur in practice. And of course, that is something very complicated to do in a complex software. You also mentioned that Fray finds a lot of bugs, but they map to about 20 fundamental root causes. I would be curious if you both Rohan and Leo, can you tell us a little bit more about these root causes and what is surprising about those, and why do you feel, developers are still falling for these pitfalls, if you will?
So yeah, as Rohan mentioned, like there are, to be honest, there are nothing new from these bugs. Like those bugs are already well studied. Like atomicity violations, like basically the developer assumes that certain operation is atomic, but apparently it's not. And while two threads are touching the same operation, then bad things happen. There's also order dependencies. Well, like developers assume there are certain orders for specific operation will happen. But in fact, if you run that in a concurrent setting, the order is not always guaranteed. I think the surprising thing we've found is actually many. You don't really need a sophisticated searching algorithm to find many bugs, and many bugs can surface even with random walk with like very small number of iterations. Here, iteration, I mean like different thread interleavings. It's just like if you run them on a normal like CI environment, you don't have access to this controlled concurrency testing environment. You're running that on a normal Linux machine, normal kernel scheduler, that bug won't appear. It's just because how the kernel schedule your program is different from how a controlled concurrency testing framework will schedule your program. So this also highlights the importance having this sort of framework where even though like we have so many advanced techniques in searching algorithm, but like having this kind of framework is still important to just surface that many bugs.
Yeah, I agree with everything that Leo said. I think one other sort of surprising code pattern that I saw in some of the bugs that we found was this notion of either spurious wake-ups or essentially like if you have code that is suspending a thread, either using APIs like object.wait in Java, or it could be like thread.park, it could be thread.sleep. There's often assumptions that some developers make that once the thread sort of wakes up from this blocking call, the state has transitioned to something good. Like the thread is woken up because there was a resource that it was waiting for, and now the resource is available, and it proceeds to do something with that assumption. But it could be the case that the thread actually is woken up before the resource was made available, and this is a very nuanced situation because it requires sort of understanding how the sort of the suspend resume APIs for things like object wait notify or thread park unpark in Java actually work. It turns out that the JVM doesn't really give you many guarantees about when these suspended threads wake up, and so you actually in theory could wake up from these pauses even before the resources that you're waiting for were actually made available. And so the correct code pattern to use is always to like check after your thread is woken up that you are in the state that you expect to be in. So simply just having a check or an assertion would have prevented some of these errors. But if in the absence of those checks, the code just keeps going, and it often it might just corrupt some data or try to like read from a null pointer, and the program would usually crash.
I see. Yeah. So I think this is one of the features that I love the most about the Fray and reading your OOPSLA paper. The fact that it proves time and time again that you don't need overly complicated algorithms to find these concurrency bugs, and still, simple algorithms can find many of these bugs. And at the same time, it also reminds us how difficult it is. And going back again, what you both said in the beginning, going back to this challenge of reasoning about time and timing in your concurrent application. And I think, this is what makes Fray so attractive and so useful. And I just have to mention this for the listeners. Fray not only finds bugs that happen in open source software that developers care about, it actually started to build a bit of a community around it. I peeked a little bit on Leo's website before this podcast, and I saw a bunch of user testimonials. So maybe, Leo, can you tell us a little bit more about this ongoing adoption effort, if you will, going from a research prototype and a research paper to an open source tool that attracts a community around it?
Yeah, definitely. So I'm always interested in building tools for real world developers. And I always I learned a lot from developers as well. So this is also the one of the goal of the Fray project itself. We are not only building a concurrency testing framework for the research community, we are also building a tool that developer can use. So that's also an ongoing effort. So we released Fray as an open source project, and we also encourage developers to use Fray. So we wrote a couple of tutorials and blog posts about how Fray can be used to test concurrent programs and how developers can integrate Fray into their testing pipeline. And also, this is an advertisement here. If you are interested in Fray and you want to contribute, definitely email us or browse the GitHub issue, grab anything you can help. So this is definitely welcome.
And listeners will have the opportunity to do that. If you go on the episode page, you will find all the relevant links to the paper, to GitHub, to Leo and Rohan's web pages, where you can contact them and join the Fray, if you will. Rohan, how do you decide, after all this, experience, both in academia and industry, and working in software reliability for so long, how do you decide a research prototype or research idea is ready to ship as a tool that software engineers can actually use?
Yeah, so that's a good question, especially because, as researchers and academics, we're sometimes, fall into this trap of, iterating on something until, we think it's perfect, and we set really high bars for ourselves and never get there. So I think it does require a balance. I mean, the more pragmatic answer is we obviously have publication deadlines. And so at some point we need to, find a logical point for the project to be considered as, mature, ready to write up, ready to publish, let's say, evaluation results. But I think the question you're asking is more from the point of view of how do we actually ship the software to users and say, hey, it's ready to be used. I think it requires sort of several steps, right? I mean, in our case, we had some early versions, almost beta versions that we made sure they work on real world code. I think that was our main target, was that we wanted to be able to work, in a push button fashion on large scale software targets like Apache Kafka, which is not at all trivial to do. And then also, once we're able to do this for a few projects, we also check that it, a sort of an unseen validation set, right? Does the tool also work on other kinds of targets that we haven't explicitly considered when developing the tool? I think that's a good benchmark to know that the tool is ready, that we don't have to keep iterating on our tool with every new target that we try to evaluate on. And once we sort of reach some convergence where every new target we consider our tool runs on just fine, I think that's good to go. But I think the other thing also is the students in my group spend a lot of time in sort of interacting with open source developers. For example, Leo spent a lot of time in debugging all of the issues found by Fray in open source software. creating, easy to understand, bug reports, providing more information to the developers to have those bugs getting fixed. I believe we also gave, a talk at some companies that were supporting this open source development. And I think I would encourage other, researchers in academia who care about, the use of their artifacts to also consider these things that are not sort of strictly required from an academic point of view, right? Like, you don't really get as many, beans, let's say, to count. That's for those who count beans on folks' CVs, like beyond your research publication. But if you do care about the community, you do care about your tool being useful, to spend the time and actually interacting with, the open source community, get feedback, write blog posts, go and give talks at like developer conferences, at like meetups, participate in interviews for podcasts hosted by eminent publishers of tech media and things like that, right? And just to make sure that you get feedback. And I think as long as you're open to that feedback, as long as you're open to allocating some time and iterating on the artifact even after the paper is published and you move on to other projects, I think that's important, and that's helped us in not only this project but other projects as well.
So thank you, Rohan, for saying this. I think many of the listeners will take all of this advice to heart. And it's certainly something that I felt in my own research, that, it's nice to have a paper accepted and counting beans as you put it. But it's also equally important to show, or not necessarily to show others your impact, but at least to have an idea yourself of what kind of impact the tools you're building have, and this kind of guides you. Maybe this could guide your next move or your next iteration of your research. I'm curious what you think about our research community, and how can our research community support more these efforts, because it's as you say, we we love counting beans, and that's not necessarily bad. I think it's just a fact of life. But I'm curious, from your perspective, can our community do more, and what should that more be?
Yeah, I think that's a great question, and it's an important discussion. I think in general, I think valuing contributions beyond just the traditional academic beans of things like publications and citations, I think is really important, and our community should strive to doing that. And I have seen changes, especially in like the systems community. There is in at least some subsets of the community a lot of respect for researchers who are actually able to deliver on artifacts and sort of show real world impact. I know this is true at CMU for sure. That's in our processes of everything from like faculty hiring to to promotions and tenure. The university has a policy of taking into account all different kinds of impact, not just traditional research publications. And I think that also stands by the recommendations of the Computing Research Association and some other sort of standards. So I think as long as the community embraces this kind of work, I think we will make more progress. Moving not just as a field in terms of science, but also in terms of acceptance by the actual consumers of our scientific innovations. In this case, software engineers, or even the end users of the software systems who care about the reliability of these systems.
That's great to hear that not only individual researchers care more and more about these efforts, but also hiring committees and promoting committees are taking into account impact more and more, and hopefully this will spark or will determine more groups to at least publish their artifacts and having their artifacts out there. And you mentioned that the systems and software engineering community and other sub communities, computer science, they have these ongoing efforts. For every conference, there is a parallel track where you can get your artifact evaluated, and that definitely helps a lot. So, which brings me to my next question: what is the next step into developing and productizing Fray? Would there be more extensions, follow up, maybe replicate the same ideas to other type of bugs? What's next?
Yeah, so there are many things. I may have a different vision that other than Rohan, but I can start with mine. One thing I noticed is not about bug finding, but about debugging. Even though Fray found so many bugs, and for each of them, debugging still take time. It's just because the software is complex, threat interleaving is complex, and reproducing certain bugs causes like many steps, and even let the developer to fully understand what happened behind the thing is still challenging. So this involves like we need to design a better debugging algorithm. Here, what I mean is similar to inside fuzzing, we have input minimization, right? So maybe for concurrency test, we also need to have some sort of like input or scheduling minimization for concurrent program to help developers to debug them. On the other hand, there's also UI UX challenges where we have debugger, we have like IDE for sequential program, but we don't really have a debugger or IDE for a concurrent program. So we are also thinking how we can build better visualization tool for developers to debug concurrent program. So yeah, this is something I feel important.
Yeah, that's I totally agree with the debuggability aspects. I think that can be improved. Another thing that we're sort of excited about as sort of the next step beyond Fray is thinking beyond just like single process multi-threaded programs, which is what Fray currently targets, but also looking at distributed applications, right? So things like Apache Zookeeper or Cassandra. These are like distributed systems. They're all sort of still written in Java, and they still are susceptible to like race condition issues. Often these race conditions are rooted not just in inter-thread interleaving, but also in interleaving across like messages over the network, through the distributed system. And so we have some ongoing, work on trying to use some of the core ideas from Fray to also test his distributed system. So we can apply these, concurrency testing algorithms, not just on inter-thread interleavings, but also on the interleavings of network messages. And that's sort of a work in progress. So, maybe we'll come back on this podcast once we have that, those results are a bit more mature. And yeah, that's the direction I'm very excited about. I also like that Leo started his answer by saying that he might have a different vision than me. I think he's now going on the tenure track job market, so this is very apt for him to have his own independent vision. And I also would be excited to see how he starts his own research group and where he takes things from there.
I'll keep a close eye on your lab and Leo's new lab, and I'm sure Leo will have more than a handful of offers to begin with beginning next year. And I'm also excited for what his vision is about debugging in general, and how developers and researchers should think about finding bugs when building software, which it's and this is an excellent segue to sort of my last set of questions, which revolve around creative process. And I think many listeners and myself included always struggle with coming up with new interesting ideas that a community cares about, or finding research problems that you can actually tackle in a few years, or a grand cycle, right? And it doesn't take a dozen years to solve, or you have to wait for a new math to be invented to solve. So I'm curious how both of you, how do you come up with these ideas beyond just reading papers and maybe using your research, your industry experience? What's your creative process? How do you scale a problem to select a problem for an appropriate project, PhD project-wise scale?
I just hire amazing students, and I hope, and I delegate the task to them. So maybe Leo can explain this. So the whole Fray project was, I think, born out of Leo's observations with concurrent programming in Java and debugging. He's like very tuned into things that the open source community is working on, and he's good at identifying the gap between like academic research and practice. And so a lot of the the main motivation of like treating applicability to real world targets as like a first class research problem, which is what Fray really does, right? We didn't invent any new algorithms or research techniques. We're just building a new platform. That entire sort of process and that entire line of thinking came out of Leo's experience, and I'm lucky to work with amazing students such as him. So I'll let Leo answer this in more detail.
Yeah, thank you, Rohan. Thank you. So actually, when I started working on this related research, I also started by designing neural algorithms. So I did my internship at Amazon 3 years ago, where we were designing better concurrency testing framework inside P. So P is a framework for distributed model testing. And because it's testing distributed system models, so it has full control over the message processing, concurrency, and like execution. So that was cool. And that was a very fun experience. And that also led me to learn that controlled concurrency testing is a really powerful tool for debugging, for testing concurrent applications. But if you look at the real world, right? Real world people write C, C++, Rust, Java, C#. They don't really write P. They only model their application in P. But when they write real world application, they still use this commercial or real world languages. But we don't see this thing exist in this like popular languages. So even though there are many research papers about this, talking about this, but developers are still using stress testing. Developers are still just write some unit tests and hope that will help them to find the concurrency bug. So having this, I think having exposed to the powerfulness of control concurrency testing, and also having observed this gap between the academic research, we all know that, and also the real world gap is help us to solve this problem, right? So we all know that control concurrency testing is a good thing, and our goal is just to bring control concurrency testing to the developers.
Awesome. So basically what you're both saying is, in order to find these interesting problems that the community cares about, you really have to be attuned to both what happened in kind of the research academic space, but also what happens in the software engineering space, and what software developers are actually facing, and what are the gaps between theory and practice, if you will. And I think that's something many of the listeners could relate to. I definitely can relate to as having a grown-up job in the distant past, and then going to research. I definitely felt this gap acutely, and I'm happy that there are researchers out there that are trying to tackle this gap in their research every day. Leo, Rohan, thank you so much for joining us today. I'm really excited to see what's next on your research agenda, and I'm more than happy to have you again on the podcast with the next project or the next set of bugs you're going to tackle. Guys, thank you so much.
Thank you very much, Bogdan, for inviting us. This was a blast.
Yeah, thank you. I'm very happy to be here. Thank you.